Swayam Prabha. Digital India. Educated India.
Welcome to our another session in this series of video lectures on Introduction to Aerodynamics. In today's session, we will continue our discussion on the non-dimensional groups. If you remember, in the last class we introduced Buckingham's pi theorem. We talked about the pi parameters, and we saw that if you are running an experiment where you have this dependency between various parameters, you can reduce the number of variables in your problem if you can formulate properly the pi groups or the non-dimensional groups. You also saw that depending on the choice of something known as the repeating variables, these pi parameters that you might obtain in an experiment or in a study could have physical significance or may not have direct physical significance. For example, if you choose the repeating variables in a certain way, you might end up with non-dimensional groups or the pi parameters, which are nothing but Reynolds number, Mach number, Prandtl number, etc. But with a different choice of the repeating variables, you might get other pi parameters in non-dimensional groups, which are important nonetheless, but may not have direct physical there is physical importance nonetheless, but in terms of what we use to assign physical importance, parameters such as Reynolds number, Mach number may not directly come out of different choice of these pi parameters, repeating variables, but nonetheless those pi parameters can also be combined in various ways to obtain physically relevant pi parameters. We will see that another approach to obtain these non-dimensional groups are through the non-dimensionalization of governing equations. In terms of when we talk about fluid mechanics or when we talk about aerodynamics, the governing equations are nothing but the equations of conservation of mass, momentum, energy, etc., applied to a volume of fluid. And we will see that depending on how you apply these formulations, the governing equations look slightly different depending on how you are formulating it, but it conveys the same physical principle. And when we start with these governing equations, we can non-dimensionalize them, and we will see that in that non-dimensional equation, these pi parameter kind of non-dimensional groups come out as coefficients in front of the differential operators, and we will see what implication those non-dimensional groups has in finding similarity between one flow problem and another flow problem, etc. In fact, if you recollect, we talk about this one situation where you want to study some flow pattern or flow problem or pressure distribution on an aircraft flying at an altitude. So, you have a certain Mach number, Reynolds number at that altitude, and you want to replicate an experiment in a wind tunnel, and you want to draw some inference based on what you have in the wind tunnel. So, the way you do is you set up your wind tunnel test in such a way that you have some matching between these similarity parameters between the wind tunnel test and the flight test. And if you can match these non-dimensional groups, which we will see are known as the similarity parameters, you will see that there is a way in which your results from the wind tunnel tests could give you insight into what is happening in the real flight condition. So, remember that you cannot just run a wind tunnel test on a similar looking model, on a similar velocity, incoming velocity, and report the results as being similar to what you might encounter in case of the real flight condition. So, we will see how we get those non-dimensional parameters, which we will call them similarity parameters. So, now if we quickly recollect what we have done in the previous class. So, we have talked about Buckingham's pi theorem. We said that if we have a physical problem, for example, in this we talked about this problem where we were interested in measuring the drag force on this cylinder here of a diameter d exposed to a flow field with free stream velocity v infinity, free stream density rho infinity and mu infinity viscosity, Then if I have to figure out the functional dependency between drag and these other parameters, I could go to the lab, set up an experiment where I vary the diameter holding density and viscosity constant, and then I measure the drag for different values of diameter, keeping the inflow velocity constant. Then I vary the velocity say in increments of 10 different increments, and then for each velocity again I repeat the same different 10 diameters. So, this way I can get a huge amount of experimental data, but the problem is if I then want to know what is the drag force on a cylinder of a certain diameter that is not in these measured test data points, or if my density of interest or my viscosity of interest falls out of this test matrix, then I am at a loss. All these experiments that I do, we have talked about how many data points we are talking about here. With all these experiments that have taken a considerable amount of time, we do not really have much value out of this experimental data, because the in the real world application you might be interested in finding the drag on a cylinder whose d or the velocity or the density or the viscosity of the fluid for which you want to measure the drag on the cylinder do not coincide with your whatever you have run your experiments for. So, extrapolation interpolation is difficult in those kind of scenarios. We said that instead of plotting the physical parameters like drag versus here drag versus the diameter, but you could have also done drag versus density or viscosity holding some other things constant. What you could have done is you could have plotted this non-dimensional group versus this non-dimensional group, and it could be shown that results from different experiments are actually collapsing on this line that gives you a functional relationship between these two non-dimensional groups. Now, the question is how do we get these non-dimensional groups and how are they relevant? So, the relevance of these things become more explicit when we look at these similarity parameters that fall out of the governing equations. Right now at least we see that these are non-dimensional groups. When you run the experiments and you get the measurements, instead of plotting the physical variables against one another, what you do is you plot the pi or the non-dimensional values against one another, and it results in a collapse of data along some functional line. So, what will happen now is if you are interested to find what is the resistance on a cylinder of a certain diameter, viscosity, etc., all you have to do is calculate this number, and then you will see that your desired point somehow falls on that functional line. Okay, that is the value of this collapse of of information. So, starting from a functional relationship between the physical parameters. Now, again I said that depending on the granularity of the problem, you can choose physical parameters, some physical parameters, but if you want, for example, in this problem I could have added. So, this is functional relationship between the drag force on the cylinder and the free stream velocity, diameter of the cylinder, free stream density, free stream viscosity, but we could have also added say the surface roughness of the cylinder. We could have added the effect of compressibility if we are talking about a cylinder at a moderately high Mach number flow. So, in those cases some additional physical parameters would come into the picture, and that would end up giving us possibly some additional pi parameters. And we in that case in this case we will see that we have just a functional relationship between two pi parameters. However, if you include more physical parameters in this problem, you might end up with a functional relationship between 3 non-dimensional groups, it can be even more. In those cases again you plot one non-dimensional variable against another, holding the rest of the non-dimensional parameters constant. So, this is the general way in which you report data. So, here we showed that applying pi theorem to above, it is possible to have a relationship of the form of pi 1 is equal to function of pi 2, where pi 1 is something similar to the drag coefficient here, and pi 2 which is the Reynolds number, the product of rho v and a physical length parameter divided by the viscosity coefficient. So, we see that using this Buckingham's pi we can go from a relationship like that to a relationship like that, which essentially is from here from 4 independent variables we move to a situation where we just have one independent variable, and when we plot these. So, the Buckingham's pi theorem, as we have seen in the last class, just gives us some of these pi parameters. It does not give us the explicit relationship between these parameters. Okay. So, that you figure out from an experiment, and here you see that it. So, this is just a hypothetical relationship between these two parameters. When you run your experiments, you will see the details of this relationship. So, Buckingham's pi just gives us the pi parameters, but not the explicit relationship between these parameters. So, we do not know how the plot will look like between when we run an experiment and plot these variables, non-dimensional variables against one another. So, then we saw that we looked at this one problem, which was kind of the method in which you apply Buckingham's pi to start from. You start from the physical relationship, you figure out the number of physical parameters, then the number of fundamental dimensional quantities. So, essentially you have to create a table like this, you have to figure out what dimensions are included in each of the physical variables. From this table, from this dimensions column, you figure out among mass, length, time, temperature and charge, how many fundamental dimensions are involved in this problem. So, you see that we have 1, 2, 3, 4, 5 physical variables, and in terms of the fundamental dimensional quantities, we have mass, we have length. So, we have mass here, we have length here, we have time here. Of course, we have these in more than one variable. So, then we have 3 fundamental dimensional quantities, and then based on the Buckingham's pi theorem we will have 5 minus 3. So, m minus n non-dimensional groups. So, this relationship can then be converted into a relationship between two non-dimensional groups for this particular problem. So, if you have say 7, if somehow m becomes 7, for example, if we include things like the surface roughness and also the compressibility effect, which might be modeled by the speed of sound inclusion in that relationship, we might have more than 2 pi parameters. And here we also saw in the last lecture how to obtain these pi parameters by using the method of repeating variables. So, you choose some repeating variables and then you create a balance of these dimensions, because these non-dimensional groups do not have any dimensions, whereas on the right hand side the repeating variables with the non-repeating variable will have some dimension, but we will force that dimension on the right hand side to be 0. So, that it matches the dimension on the left hand side, which is the dimension of a pi parameter, and that way we can get terms such as so pi 1 and then pi 2. Now, we said that instead of choosing these as repeating variables, what if we choose something else as repeating variables? The answer we saw is that you still have these non-dimensional groups, but it is possible that these non-dimensional groups will not be the common non-dimensional or the similarity parameters that we typically talk about, Reynolds number, Mach number, drag coefficient, etc. But still they will be useful in terms of reduction in the number of variables in an experiment, the number of independent variables in an experiment, the collapse of data also will be there, and it can be shown that this pi 1, pi 2, if you multiply this by some constant, if you raise it to some power, if you take a product of those two raised power or multiply it by some constant values of pi 1, pi 2, the resulting product will also be a non-dimensional number, non-dimensional parameter. So, sometimes you, depending on the choice of your repeating variables, you might get pi 1, pi 2, pi 3, which are physically relevant, like the Reynolds numbers, drag coefficient, etc. Sometimes you, for example, these drag divided by mu v infinity d does not have a very formal name in terms of the parameters that we really talk about, and we will see what are these similarity parameters and how they fall out from the governing partial differential equations. Okay, so, we in the last lecture we also looked at the speed of blast wave, as G. I. Taylor in 1950 applied these these non-dimensional the pi Buckingham's pi theorem approach, also known as dimensional analysis or similitude, to finding out the the amount of energy that was released in these atom bomb explosions. We also saw that the time period of a simple pendulum can also be obtained using the Buckingham's pi theorem approach. And of course, we are interested in something of the sort of the force on an airfoil or a wing. And here, for example, you can, so the way you do this one, again this is another specific example of what we have already seen before. So, first choose pertinent variables that are important to the problem. So, here we see that the force on this wing cross section depends on physical parameters such as the v infinity, rho infinity, mu infinity, a infinity. We will see that if you want to bring in the effect of compressibility, you can use a infinity as a parameter as well. And then this angle of attack, you can include it as a non-dimensional parameter in the final form, because if it is in radians, it is dimensionless. So, 6 physical variables in this problem, 3 fundamental dimensions. So, we will have 6 minus 3 or 3 non-dimensional groups. So, given this situation, we will seek something like a relationship between 3 non-dimensional groups. So, if you choose rho, v infinity and c, c being the chord length of this wing, then you can get 3 of these pi parameters, and we will see that essentially it will result in these 3 similarity parameters. In fact, if you see your pi 1 is r by rho v infinity square c square, that one can be adjusted. So, see, I have multiplied it by a constant, it is a non-dimensional number, just it is half with the 20 dimensions. So, as I said, you can raise pi 1 to some powers, you can multiply it by some constants, it still is a valid non-dimensional group. So, here we, instead of pi 1, which is this, we can use, we can slightly modify this parameter and get something which is of physical relevance. So, if you remember, this is the drag coefficient or the force coefficient. So, r divided by half rho v square into some area term. Okay, see, this area term and this c square term have the same dimension. So, we can use that physical information to get a modified pi parameter that has some physical sense. So, this one, although this would give the collapse of data and would reduce the number of independent variables in your experiment, would also allow you to interpolate and extrapolate and get results for like a airfoil section of a different chord length in a unknown velocity v infinity rho infinity situation. But nonetheless, we often modify these pi parameters based on multiplication with constants, raising to the power of things to get pi parameters that have some physical significance. So, here we see pi 1, we adjust it slightly to get the drag coefficient. Pi 2 is rho v c by mu infinity, which is nothing but r e infinity. So, we see that pi 2 luckily becomes we do not have to make any adjustments, we get this pi group and we quickly recognize that it is what we know as the Reynolds number. And pi 3 also we see we do not need any adjustment, it is a relation, it is a ratio between v infinity and a infinity, which is the Mach number. So, from this form we get the drag coefficient, or rather the force coefficient is a function of all this. If we include, so this one would, if you try to find the drag coefficient as a function of Reynolds number or Mach number. You would fix your wing in the wind tunnel in a certain orientation. So, at a fixed angle of attack, and then you would measure all these values. If your angle of attack is also varying, then you can include alpha as a one more non-dimensional parameter. Okay. So, alpha is a non-dimensional parameter that you can directly include in this functional relationship. Now, in your aerodynamics lab in the second year, you will come across this experiment where you measure or you report CD versus Reynolds number on a cylinder, circular cylinder mounted in a wind tunnel. And you will see, of course, you have this is a very extended plot. You see that the Reynolds number ranges from 10 to the power minus 1 all the way to 10 to the power 7, and so you see a huge amount of range has been covered in this plot. And in this region we have the Stokes flow regime, where you have very high viscous drag. However, for aerospace applications, typically we are looking at Reynolds number in the range of somewhere in that range, and in your experiments you might be fortunate enough to see this functional relationship between CD and Reynolds number, where you see this sharp fall in drag around a certain Reynolds number. Say around that Reynolds number you see that very precipitous drop in CD. Of course, if you want to calculate drag, if you want to calculate velocity, you can use CD, use the dimensions and some known parameters, and from these non-dimensional groups you can still go back to the physical parameters. Okay, it is not that once you move to the non-dimensional groups you are losing track of the physical parameters. So, the non-dimensional groups are just helping you to have less number of independent variables. So, lesser amount of test metrics to run your tests at, and also it gives some inherent or underlying trend between these non-dimensional groups, which has physical significance, and it leads to the collapse of data points on that particular functional line. Now, when you run your experiments and you see this, and you perhaps run a flow visualization study to figure out why that sharp decrease in drag CD is happening, you can actually see that it is really because of the difference between in these regions you have this large wake forming in the downstream of your circular cylinder. If you remember our study of pressure drag due to flow separation, this is what we were talking about, that when you have a separated region, the pressure in the separated region does not recover to what it should have recovered to balance force between the fore and the aft side of the body. So, in this case, since you have a large separation, the pressure on the surface of the cylinder in this, say somewhere from here to here, so in this entire region is lesser than what should have been there to balance the force in the relative wind direction in the aft and the fore sides. So, here we do not have enough force to oppose the force from the front of this cylinder. On the other hand, as we increase the Reynolds number, what happens is we end up there is a laminar boundary layer separation, but then there is a reattachment, and then there is a turbulent boundary layer separation, which eventually results in a smaller wake. So, you see that when you run these experiments and plot things against these non-dimensional groups, data collapses on some functional relationship line, and that can give you some insight into what is happening in certain ranges of this non-dimensional parameter. Over here, I think we have discussed this thing already. If you did not have flow separation, if we are talking about inviscid flow, then your pressure distribution would look something like the black line here. So, it is inviscid and incompressible as well. I think you need to apply Bernoulli's theorem to find the pressure on the surface, and you get something like this, which is the theory work. However, in these two cases, you see you have, so the supercritical is what is happening here, and the subcritical is what is happening here, and you see that the pressure in the subcritical stays somewhere here, whereas for the supercritical pressure can rise a little bit more to balance the gulf between the fore and the aft of this cylinder, and that results in the increase in C d at this higher Reynolds number. So, C d falls because the large wake switches to a small wake. So, you see that when you run an experiment and you identify the proper non-dimensional groups, some of these physical insights is often revealed, because you have this data collapse on this functional line, and you can run a lot of a wide range of tests to get some trends at different ranges of the non-dimensional parameters. Okay, now, this is what I wanted to discuss in today's lecture. So, this Buckingham's pi theorem gives you some non-dimensional parameters that are relevant for a problem. If you are lucky and you have chosen your repeating variables in a proper way, I mean not in a proper way, but if you have chosen your repeating variables in a certain way, you might end up getting non-dimensional groups that have this physical significance, which we commonly might use as Reynolds number, Mach number, etc. However, you can also get these non-dimensional groups from the governing equations, and we will see that this has a very important insight. This gives a very important insight into something known as dynamic similarity. Okay, so, I have added this term dynamic similarity. So, this is the same problem that I am talking about, I talked about in the start of the class, that how do you say that this experiment that you are running in a wind tunnel, the data that we get from the wind tunnel can be used to obtain information on a vehicle that is flying at 30,000 feet at a certain Mach number, or rather how do you plan your experiment in a wind tunnel, so that it gives you information that is useful for understanding what is happening with a real flight condition at a certain altitude, Mach number condition. So, we will see that there are things called similarity parameters. These are nothing but the pi parameters kind of things that fall out from the governing equations, and when two problems have the same similarity parameters, or rather when two problems have the same values for the different similarity parameters, then we can expect some dynamic similarity between these two problems, given the two bodies have similar geometrical shapes. Okay. In some cases, the surface temperature of the body also becomes important, but we will see those things later. But nonetheless, similarity parameters are obtained from governing equations through a process of non-dimensionalization, and when two physical problems say flow on a small airplane in a wind tunnel and flow on a real scale full scale 747 flying at 30,000 feet, there is a certain way in which if the two objects are at least geometrically similar, there is a way in which you can make sure that the data you collect on that small aircraft in the wind tunnel will give you data that is relevant for the big 747 flying at altitude at the given Mach number. So, before we so I also said that you use your governing equations to obtain these similarity parameters. So, we will see what is meant by governing equations. For Buckingham's pi theorem, we really did not need a governing relation. All we needed was an rough idea of what are the relevant physical parameters important for the problem, and which physical parameter we are trying to make the dependent variable, which physical parameters we are trying to look at as independent variables, and then even without knowing the functional relationship, we could obtain the important non-dimensional groups. And in cases where you had just one or two non-dimensional groups, you could really run your test and find the functional relationship between these groups. Now, on the other hand, you can start with governing equations. So, Buckingham's pi does not need governing equations, you just need what are the physical parameters that are important for the problem. On the other hand, you can apply a similar approach. We will see it has some similarity in terms of isolating these non-dimensional groups, but it is not, of course, it is not similar to Buckingham's pi theorem beyond that. But so, to understand this, let us first quickly look at what we mean by governing equations. Okay, so, we said that similarity parameters will be obtained from the governing equations. Buckingham's pi theorem, similarity parameters or these non-dimensional groups were obtained from just a functional relationship between things. We did not, or rather the identification of the relevant parameters for the problem. We did not care about the functional relationship. We just noted down what are the physical parameters, and through some technique we figured out what could be the non-dimensional groups relevant to the problem. Here we will start with governing equation, and we will get these non-dimensional groups which will be known as similarity parameters, and we will argue that if two physical problems like the flow on the real 747 at altitude and wind tunnels, subscale model of the 747 in a wind tunnel, if they have the same values for the similarity parameters, it can be shown that the data that you obtain on this wind tunnel test will be relevant for understanding flow on the real flight condition. So, first of all, let us see what are governing equations. Now, of course, the English word itself is quite explicit. Governing equations are constraints on physical parameters that govern a certain physical problem. For example, F is equal to ma, you can talk about it as the governing equation for force mass acceleration balance. So, this is a governing equation from Newton's laws of mechanics, Newton's laws of motion. In case of fluids, we will see that there are several governing equations. We have, if you apply the principle of mass conservation, you will get something known as the continuity equation. Okay. So, continuity equation is based on the principle of mass conservation in a fluid flow problem, and this gives us an equation of conservation of mass which is popularly known as the continuity equation. Secondly, if you take a element of fluid, and we will say what kind of element of fluid, you can take a differential element of fluid, you can also take a finite volume of fluid. Your differential element can be fixed in space or could be moving with the flow. Again, your finite volume fluid element can be fixed in space, or rather the region can be fixed in space, or it can flow with the fluid. So, we will show that depending on whether you derive these governing equations using a differential element or a finite element, or rather a finite volume element, whether it is Eulerian frame or Lagrangian volume, we will see that you will have different forms of the equations, but because the equations are talking about the same thing, inherently they are similar. Okay. Although they might look different depending on how you derive them, inherently they will be the same thing. So, mass conservation will give you continuity equation, force momentum balance will give you Euler equation if you are working with force momentum balance in the inviscid sense. So, remember we said a fluid can have viscosity, but in certain regions where the gradients of velocity etcetera are not large, the flow behaves like inviscid, and there Euler equation, which is essentially the force momentum balance equation, will have the viscous terms will not be there, and this becomes the Euler equation. So, governing equations, you apply the conservation of mass, you get the continuity equation, you apply force momentum balance without viscosity, you get Euler equation, you work with force momentum balance including viscosity, you get Navier Stokes equation. So, you understand that both of these are momentum equations, but Navier Stokes include the viscous forces, or rather forces due to the inclusion of viscosity. Remember, we talked about the shear stresses. So, shear forces are there if you include viscosity. So, if you include viscosity, you will end up getting the Navier-Stokes equations, and then if you apply the principle of energy conservation again on that infinitesimal fluid volume or fluid volume of finite expanse, you can get the energy equation. And so, we see that non-dimensional groups with physical significance, which when similar between two flow problems, indicate that the non-dimensional variables when plotted against non-dimensional coordinates will be the same. Okay, let us wait for this portion till we see what really we are talking about. So, first of all, let us focus our attention on the governing equations, because we will see that. Okay, let me at least show you what is going to come out of all this work. Okay. So, if you see this one, we will see this looks a little cluttered in this particular slide, and for those who are interested to go through this material on their own, you can look up chapter 6 . Okay, chapter 6 of hypersonic and high temperature gas dynamics by John Anderson. Chapter 6 deals with viscous hypersonic flow. So, of course, this is advanced topic, but nonetheless these governing equations are there. So, essentially any kind of real flow problem will have the same governing equations to begin with. So, here you see we have the continuity equation, which is a statement of the conservation of mass. So, you apply conservation of mass to an infinitesimal fluid element or to a finite expanse fluid element, you get a governing relationship which is known as the continuity equation, and it looks like this. Okay, you see okay, so that is the continuity equation. Now, I must say that this is the differential form of the continuity equation. There is also an integral form of the continuity equation. So, depending on how you derive these equations, it can have various forms, but it is the same principle or it is equivalent. So, we can show that your differential form of the continuity equation, which is this what is shown here in this slide, can be obtained from the integral form. So, the integral form of the continuity equation looks very different, but using appropriate mathematical tools we can show that integral form is nothing but same as the differential form. The forms are different, but one can be obtained from the other. So, there is equivalence in terms of the message that they are conveying. Next, we have the Navier-Stokes equations, which are nothing but the x, y, z momentum equations, where viscosity has been considered. So, you see that. So, first when you see a complicated or at least a cluttered page like this, you want to move slowly and see how much of it you can identify. So, here for example, you see that we have the capital D by dt. Okay. So, we will show how these things are derived, but at this point I just want to introduce the idea that starting from the governing equations, what you see in this page, we can move to something which is known as the non-dimensionalized form of the governing equations, and we will see that those non-dimensional groups fall out from this non-dimensionalization process. So, you see that the substantial derivative, as you can see here, substantial derivative of u component of velocity, substantial derivative of the v component of velocity, substantial derivative of the w component of velocity can be related to these forces that are acting on that fluid element. Okay. So, this is the continuity equation, these three form the Navier Stokes equation or the momentum equation. If you want to neglect viscosity, then these shear stress terms will drop out, and what you will end up with the Euler equations. Okay. So, Euler equations are nothing but these momentum equations without the viscous force, hence without the viscous stresses included in the problem. And then we have the energy equation, which again is a total derivative of internal energy plus v square by 2 kinetic energy contained in that infinitesimal volume of fluid, and it can be shown to be something like this. And this one we will talk about these things in detail, but at this point let us just accept this as the governing equation. We will derive these things in subsequent lectures, but at this point you can think of it this way, that the material derivative. So, whenever you have material derivative, you understand that you are working on a Lagrangian approach. So, you have this is a differential form of the governing equations. So, essentially you have an infinitesimal volume that you are considering, and for the momentum and the energy equations, what you do is you take a infinitesimal fluid volume dx dy dz that is moving with the flow. Okay. So, that is why you do the material derivative with respect derivative with respect to time, and you can show that this kind of a constraint exists, okay, between momentum and force, between energy. So, here for example, what we are saying is the energy in this infinitesimal element of fluid of fixed mass identity, as it flows through the fluid, the rate at which it changes has to do with the rate at which heat is being given or taken away from that chunk, the rate at which heat is flowing into or out of the chunk due to thermal conduction. You have the pressure volume or pressure velocity work. We will see all these things at this point, at least so that you understand some of these what are all these terms without really getting into the details of it. Here you see some product of velocity and some shear stresses. So, you can kind of imagine that it could be something like work done by the shear forces. So, work is force into displacement. So, when you do force into velocity, it is essentially force into displacement by time. So, it still has that element of work per unit time kind of thing. So, all these terms are products of velocities and corresponding shear stresses and forces. So, those are the work done by the viscous forces. So, these are contributions arising from the work done by the viscous forces. This is work done due to the pressure forces. This is energy entering leaving due to thermal conduction. You see temperature gradient in the x direction, etc. And then this is the volumetric heating or cooling that this infinitesimal element is experiencing. So, that is your energy equation. Okay. And then I think this is something that you might have done already from your course in fluid mechanics, that the shear stresses can be related to the rate of strain using these relations, and the compressive stresses can be obtained through these expressions. Okay. So, we will get into this thing, but what I want to show you now is, so we somehow say this requires a like a series of lectures, and sometimes it might be a better idea to introduce this Reynolds transport theorem before we really get into a rigorous derivation of these governing equations. Although Reynolds transport theorem is used when we are trying to derive these governing equations in their integral form, the derivation of governing equations in their differential form, which ends up in what you see on this page, it is not necessary to introduce Reynolds transport theorem at the beginning, but if I introduce Reynolds transport theorem, then I discuss the integral forms of the governing equations, and then I show that the integral forms can be somehow tweaked and massaged into these differential forms, then you will have more conviction that the differential forms and the integral forms talk about the same things. However, here since we are trying to still continuing our discussion on these non-dimensional parameters that are of relevance to physical problems, I wanted to bring this in. So, these derivation that you see on this page does not require Reynolds transport theorem understanding. We can still take a small dx dy dz element, apply the mass conservation or energy conservation or momentum conservation principles on that differential element and get these forms, get these expressions. That is not the focus of this lecture. Okay. Our focus right now is, given that we have these governing equations, what we do is, so we have these things on hand. Okay. So, the governing equations are given. Right now, you have at least you have some idea of what is happening. This one is a momentum force balance, this one is energy change of energy of a parcel of fluid that you are following, because you are using the substantial derivatives, and you are saying that these rate of change of energy of this fluid element that you are following has to do with all these things that are happening on the right hand side, some volumetric heating or cooling, some heat transfer through conduction through the surfaces of that fluid element, some pressure volume work, and some viscous stress derived work. Okay. So, when you multiply force by velocity, you get work by time, and then that can be related to how the energy in your chunk is growing or decreasing over time. So, now we have these equations. So, what we do here in the next slide is, now we replace. So, the previous expression had constraints between density, velocity, pressure, etc. What we will do now is, we will replace density by a non-dimensional density, okay. And to get that, we will use rho prime, which is the non-dimensional form of density, is equal to rho by rho infinity. So, what we are doing is, we are using some of these free stream values and then some geometrically relevant values to non-dimensionalize the governing equations. Now, this is of great importance and we will see why. So, you start with the governing equations in their dimensional form, then you non-dimensionalize the governing equations in such a way that you replace the dimensional density with the free stream density, you replace the dimensional velocity with the free stream velocity, and this is a non-dimensional x component of velocity, so non-dimensionalized y component of velocity, etc. So, now if you plug these things, so if you plug all these things into the governing equations, what you will get is, you will see that now you have a continuity equation in terms of the non-dimensional variables. Interestingly, for the continuity equation, the non-dimensional form of the continuity equation is same as the So, here this is, so here we have made some assumptions, because otherwise this thing gets extremely out of control to actually show or to write on a single page. So, what we are doing is, we are assuming a steady problem. So, what that means is, this term drops out. Also, we are making that a 2D assumption. So, of course, you can have a 3D problem, you can even have a problem where things are varying only in one dimension, but we are restricting ourselves to a 2D assumption. So, if you expand this one and you drop the time derivative and you also drop the dependency on the, say, on the z direction, and you apply this non-dimensionalization, you end up with a form of continuity equation that looks something like this. Okay, so, it is actually quite simple to observe this thing. So, starting with this, setting this to 0, because we are now saying okay, let us look at a steady problem, and then we expand this. As you understand, this is the divergence of this vector rho times v vector, and then so essentially this becomes dou by dou x times rho u plus dou by dou y times rho v plus dou by dou z times rho w. But then again we are saying that we are looking at a 2D problem. So, that dou by dou w drops out. So, essentially you get this form, and then when you put in your non-dimensional groups at the non-dimensionalized variables, we end up with the form of the continuity equation that looks like this. We will talk about how this governing equation is derived in the first place later on. Over here you see, now this is where some interesting things start happening. So, here what is happening is we have applied the same approach to the x momentum and the y momentum equation. Okay. We are not talking about the z momentum at this point, because again we said that we are looking at a steady and 2D assumption. So, when you first you look at the steady problem, then you remove the z dependency or the z momentum equation. Of course, you also remove the z dependency from the x and the y components. Again, those things we will look at a later point. But now, if you start with the x momentum, y momentum, you make them, you modify. So, this is with the dimensional variables. First, you create the dimensional variable problem for the steady 2D, and then you use these non-dimensional groups. So, it is actually quite simple. So, what you do is, instead of rho, you write rho infinity times rho prime. Now, since rho infinity is constant, you can take it out of the derivative sign. So, that is how we get these expressions. Okay. So, all you do is you go back to these expressions, replace p by p prime times p infinity, then take p infinity out, replace y by y prime times y infinity, or say y prime times c, and then you take c out. Okay. So, that is how you go from here to these forms. Now, what is interesting is, while in the continuity equation the result did not have any interesting coefficients. So, coefficients are 1 for both of these. Here you see some interesting things are starting to show up. Okay. So, what is happening is, all these rho infinity, v infinity, p infinity, etc., that you are using to get the non-dimensional version of the equations can be collected in front of these differential operators, and you get these non-dimensional groups. See, in Buckingham's pi theorem, we started with, we did not care about the governing equation. Okay. So, we just started with the functional relationship between a few parameters. Then we apply, we figure out that for this problem there will be so many non-dimensional groups, and we obtain them with the use of the repeating variables, etc. In this case, this one is more revealing. So, you start with the governing equation. Governing equations can be of based on conservation of mass, momentum, energy. From the dimensional forms of this equation, you replace, you try to convert that into a non-dimensional form, and the way to do it is, you replace these dimensional variables by its non-dimensional counterpart by dividing it with some reference values. So, here your rho infinity, v infinity, p infinity, these are all and others that you are using to get the non-dimensional versions of these variables are known as the reference variables. And then when you collect, so you see your these physical terms, these Mach number, Reynolds number, Mach number, Reynolds number, and in this case another interesting term which is known as Prandtl number. So, this is the energy equation. when you are non-dimensionalizing the energy equation, of course, now you see that the equation has all non-dimensional variables, okay. But some of these, the dimensional, the reference values can be collected and they appear as coefficients in these expressions. So, you see here your reference values become m infinity by r e infinity square, sorry, m infinity square by r e infinity, you have gamma here which comes out. So, what happens is you have non-dimensionalized governing equations with coefficients that actually come from the reference variables. Okay, so, in the previous, so in this slide you had governing equations that were based on the dimensional variables. In this page, of course, we have restricted to steady and 2D. So, you have to incorporate that thing in the governing equations, but once we do steady and 2D assumption and then we convert from the dimensional forms of these governing equations to the non-dimensional forms, what happens is the reference quantities like this actually clog together in front of the derivative signs and fall out like this. So, here we have the, so m infinity is nothing but v infinity by infinity, r infinity is rho infinity v infinity mu infinity by c. Remember that we have used rho infinity v infinity mu infinity to non-dimensionalize some of these dimensional parameters to get the non-dimensional form. Prandtl number is something that you get in heat problems where that energy equation is comes into the picture. So, now what I want you to imagine is, suppose you have two problems that have the same governing equation in terms of these non-dimensional groups. So, any flow problem will have can be, so any steady 2D flow will be governed by these equations. Now, if I tell you that these two flow problems, so any flow problem will be governed by these equations, okay, any steady 2D flow field. Now, I am saying that we are looking at this flow in the wind tunnel, flow at 30,000 feet. Of course, it is not a very 2D problem, that assumption may not be the right assumption, but let us think that we have a wing in a wind tunnel, which is we are looking at a 2D problem, and we have a very large wing exposed to a very high velocity, and we are trying to create some analogy between the two. Now, these two flow problems are guided by the same governing equation. On top of that, if these things give you the same numbers, okay, so suppose for the small problem, small wing problem and the large wing problem of similar geometrical shapes, somehow the Mach number m infinity, r e infinity and p r infinity and gamma are coming out to be the same. Okay. So, you see m infinity is a combination of v infinity divided by a infinity. So, for your small experiment in the wind tunnel and for your very large wing in a very high stream of flow in the real scenario, your v infinity may be different, your a infinity may be different, but as long as your v infinity by a infinity is the same between these two flow. Similarly, as long as your r e infinity is same between these two flow. So, individually my rho infinity, v infinity, mu infinity and c can be different between these two problems, but as long as that combination is the same, what we have is non-dimensional forms like this with the exact same numbers for the two problems. Okay, so, we have the same non-dimensional equation with the same non-dimensional coefficients in front of some of these derivative signs. Then you can guess that maybe the results from these two would be the same, and that is precisely what is meant by similarity parameter and these dynamic similarity. So, if these things are the same between these two problems of the small wing in a small v infinity air and a large wing of similar geometric shape. We will talk about what is this relevance of this similar geometric shape at a very high wind, but the Reynolds number, Mach number, Prandtl number, gamma etc. for this problem matches with the gamma, the Prandtl number, Reynolds number and Mach number for this problem, then it can be shown that if you plot p prime versus x prime, or if you plot u prime versus y prime, they will be the same between these two problems. So, non-dimensional parameters when plotted against each other for this problem will be similar to non-dimensional, the same non-dimensional parameter. So, suppose p prime versus x prime here and p prime versus x prime here will be exactly the same thing, and we will see why that happens in the next class. Here I just wanted to introduce the idea that if you start with governing equation, you non-dimensionalize them, there are some combinations of these free stream parameters that come in front of the derivative signs. If they are the same between two problems, now there is the extra requirement that the boundary conditions or the non-dimensionalized variables that define the boundary conditions, they have to be same between the two problems as well. But we will continue with this discussion in the next class, and we will also see how the governing equations are derived in a little bit greater detail, and in the subsequent classes we will talk about Reynolds transport theorem, derive the integral forms of the equations, and once again see how they lead to the differential forms that we are going to talk about or touch upon in this lecture and in the subsequent few lectures. Thank you for your time, and see you in the next lecture.